Right, well, let's go back and take another look at Pat and Kim and their racing problem here. So, as you recall, Pat and Kim are in a race. Pat's racing at 8 miles per hour. Kim races at 6 miles per hour. They're in this race. Pat finishes 25 minutes earlier, and the question was, how long is the race? Let's review how we went over doing that. The first thing we did was we took Pat and Kim's speeds in miles per hour and turned those into minutes per mile, which is actually a pretty common calculation when you're dealing with running. So, let's see, 8 miles per hour. We flipped it upside down to make it 1 hour per 8 miles. Then we changed 1 hour into 60 minutes to be 60 minutes per mile. And then we essentially just divided to get 15 halves minutes per mile. Or because we simplified the fraction. We could have also turned it into a decimal, but I chose not to turn it into a decimal here, simply because I wanted to represent a method that's more versatile. If our denominator had turned out to be like, say, a 3, for example, then you wouldn't want to turn it into a decimal, because that would give you a repeating decimal, introducing error into your equation if you have to round it off, which you would. Okay, Kim was 6 miles per hour. Flip it upside down. We get 1 hour per 6 miles. Make that 60 minutes per 6 miles, which we simplify down to 10 minutes per mile. Then after that, we filled out this table where we just looked at different mile amounts. And since we know how many minutes it takes each of them to finish a mile, then I just take that minutes per mile rate and I multiply by the distance to get different amounts of minutes it takes them to go that far. So say, for example, it took Pat to go 2 miles. It took Pat 15 minutes. And it took Kim 20. We just subtract to get a difference of 5. Right? Then we tried 4. For 4 miles, it takes Pat 30 minutes. And it takes Kim 40 minutes. So this is 7.5 or 15 halves times 4. And here we have, times 4. And then 10 minutes per mile times 4 miles gives us 40 minutes. And there's a difference of 10. And we just kept going along until we finally found that at 10 miles, it takes Pat 15 halves times 10, or 75 minutes. It takes Kim, if I say Pat takes that long, it takes Kim 10 minutes per mile times 10 miles, or 100 minutes, and therefore the difference is 25. So the procedure here was to take the number of miles that we're guessing, and then multiply that by Pat's minute per mile rate and Kim's minute per mile rate, subtract the two, and find the difference. And we just kept looking until we found the difference we wanted. So if I want to turn that into like a more like a versatile setup, something where I could plug it into a machine and let the machine do all the work. And then maybe I also want to do it for different finish times. So, I mean, the guess and check table we did worked out pretty well for 25 minutes, but what if the difference had been like, say, 24 minutes or 23 minutes? Then it'd be kind of hard to find on the table because it wouldn't have been a whole mile amount. It would have been some like, 9.8 miles or 9.7 miles, and it gets more complicated. So what we want to do is come up with a method where I can just start with any difference in finish times, which we'll call M, and use that to calculate D, the total distance of the race, based on Pat's speed, which is 8 miles an hour, and Kim's speed, which was 6 miles an hour. So remember, that turned out to mean that, hold on a second. Okay. So Pat's speed was 8 miles per hour, but that turned into 60 over 8 minutes per mile, which was 15 over 2. And Kim's speed was 6 miles per hour, and and the speed is a rate. I'm just rewriting this. Kim's rate in minutes per mile was 60 over 6, or 10. So we want to remember, as we're going through this, where 15 halves and 10 came from in the first place. All right, so If you recall, our procedure was to take the distance of the race. Well, we'll just make a little mini table here. All right, so we had distance, which is called M, or I'm sorry, D. All right, distance, which was D. And then we had Kim's time. Put time Kim, Pat, and then difference, which we'll call M from up here. Right. So when we found the correct time, we guessed 10. To get Kim's time, we did 10 times 15 over 2. And to do Pat's time, we did 10 times 10. Or 10 miles times 10 minutes per mile. And we found the difference, which was we took 10 times 10, that's Pat's time, the longer time, and we subtracted 10 times 15 over 2, which is Kim's time, to find the difference, which turned out to be our difference in finish time that we were looking for, which was M. And here essentially is our formula, except instead of 10 here and 10 here, I'm just going to replace those with our D for distance. Okay. So let's rewrite our formula down here. It's going to be 10D minus 15 halves D equals M. So this is, let's just break this down what these are. The first 10 is Kim's rate minutes per mile. And here is Pat's rate minutes per mile. The D's are the length of the race in miles, and the M is the difference in finish times in minutes. So, and of course, if I take minutes per mile and I multiply it times the number of miles, and look, this is already doing like a unit analysis. If I take minutes per mile, that's like our 10 here, and I multiply by D, which is the number of miles, like this, then miles cancels with miles, and I'm left with minutes. So that's how 10 times D becomes Kim's time. And this is how 15 halves times D, so it's minutes per mile times miles, gives us another number of minutes. That's Kim's number of minutes, and I subtract one from the other, and I get the difference between them, which is how much faster Kim finished the race than Pat. But the problem with this formula right now is that I want to be able to plug in a number of minutes and then output a number of a distance of the race. I want to say, well, okay, if Kim finishes 25 minutes earlier than Pat, I want to plug in 25 and I want to output how long the race was. And as it is now, it doesn't really work very well that way. I mean, I could kind of do it. I could input a number here, but I have to do some algebra afterwards. And I don't want to do that. I just want to be able to plug it in, evaluate the expression, and then be done with it. So we're going to have to rearrange this formula so that D is all by itself, but that's not too terribly difficult. So let's go down here. I'm going to rewrite it. 10D minus 15 halves D equals M. So I'm going to do kind of a reverse distributive property thing here. I'm going to pull those two D's out. over here, and I have 10 minus 15 halves. Okay, so if I were to multiply this back in, d times 10, d times 15 halves. And then let's divide both sides by this whole amount right here. Now 10 minus 15 halves. So 15 halves is 7.5. 10 minus 7.5 is 2.5. Right? So this really is just a number. It looks terribly complicated, but again, it's just a number. And I can divide both sides by that number. And I end up with d equals m over 10 minus 15 halves, which is really just d equals m over 2.5. So now I have my end formula, and all I have to do is just plug in a difference, and I get a length of the race, which would be easy enough. We could check here. D equals, let's plug in 10 miles. 10 divided by 2.5. Hold on a second. Oh, sorry. What I meant was a number of minutes. So the difference is 25 minutes. 25 divided by 2.5 is 10 miles, which we found from our table. Let's plug in some other numbers. Let's see, we had here on our paint that if the difference was 5, then they must have been 2 miles apart. So I could plug in 5 into our formula. D equals 5 over 2.5, and that equals 2. So it works. We can test it out on some more, but we see it works every time. Now, before we go any further, let's say you even wanted to make this formula more versatile and make it work for any speed that Pat and Kim might have. So in that case, you look down at our final result here. The 10 here was derived from Pat's speed, Kim's speed, and the 15 halves was derived from Pat's speed. So at this point, we just take, those numbers there, and we could write them as expressions. Where do we get those expressions from? We got them from up here. Here's the number for Pat's rate. Here's the number for Kim's rate. Here's how we calculated those: 60 over 8 and 60 over 6. And the 8 comes from Pat's speed, and the 6 comes from Kim's speed. So I could start with any speed, right? And I would just have to replace them over here, simplify if possible, and then go down to our end formula, and there they show up again. So I could rewrite this formula using any two speeds I wanted to. Right? And that's the end of that.